At Smokeless Chimney, we are attracting some interns, and I would like to highlight some of those interns. Today, it is...
My name is Aditya Zaware and I worked on the technical review of the Smokeless Chimney project.
When they come to us, we don't know much about them, so I give them some documents, like the CRADA project we worked on and a few other things, and we ask them to come up with a 2-page summary so that I can say they understand the material. After reviewing the pitch and the CRADA report, I see that Smokeless Chimney aims to tackle a real environmental issue. Residential stoves often emit high levels of particulates when combustion is not optimized. Although wood is a renewable energy source, inefficient burning produces smoke that harms air quality and public health. Rather than eliminating wood heating, the company is advocating combustion efficiency through real-time optical monitoring and adaptive control systems. Particulate matter from residential heating contributes directly to localized air pollution, particularly during winter when atmospheric conditions trap emissions near the ground. Poor combustion wastes fuel and increases the release of fine particles capable of penetrating deep into the lungs. By focusing on combustion performance rather than fuel replacement, the company approaches the issue from a systems perspective. The strategy is not to remove wood as an energy source, but to extract energy from it more efficiently and cleanly. The development of the octa-ring sensor is central to this approach. Rather than relying on complex laboratory-grade particle measurement systems, the sensor evaluates smoke opacity in the chimney by measuring light absorption and scattering. Opacity functions as a practical proxy for combustion quality because incomplete burning produces denser smoke that absorbs and scatters light more. By interpreting this optical interaction, the system can infer combustion efficiency in real time. The measurement does not remain passive. The collected data informs airflow adjustment within the stove, creating a feedback mechanism that reduces smoke while enhancing combustion performance. In effect, the system operates as a closed-loop control model in which measurement and adjustment continuously interact to optimize output. At first, I questioned whether improving wood stoves was necessary when electric heating systems exist. However, in very cold regions such as parts of the United States and Europe, heating demand is constant and electricity costs can be high with unplanned outages. Wood remains locally available, affordable, and renewable when responsibly sourced. In that context, improving stove efficiency is economically and practically viable. Energy transitions are rarely immediate. Infrastructure costs and cultural habits shape heating decisions. From the DOE-funded research project with Lawrence Berkeley National Laboratory, the concept demonstrates strong technical validation while continuing refinement toward large-scale optimization. The opacity measurements demonstrated strong correlation with laboratory-grade instruments across multiple test conditions, supporting the technical feasibility of smoke monitoring approach. This validation confirms that a simplified optical method can reliably approximate more complex particle measurement systems. While laboratory validation confirms technical feasibility, long-term field deployment requires addressing environmental variability inherent in real-world chimney systems. These environments introduce variables that are difficult to replicate in controlled testing conditions. Temperature fluctuations, fuel variability, user behavior, and environmental exposure all influence combustion dynamics. For the system to function reliably outside the laboratory, measurement stability must remain consistent despite the changing conditions. One key engineering challenge, temperature drift, has been addressed through the integration of a newer technology sensor. Chimney environments experience significant thermal variation. Calibration consistency is another critical factor. If the system is deployed across many households, it must maintain reliable readings without requiring frequent manual recalibration. Durability is equally important, as prolonged exposure to soot ash and thermal cycling may impact optical clarity and sensor alignment. These engineering refinements indicate that the project has progressed far beyond the purely conceptual stage and is now focused on optimization for reliable deployment. The underlying concept has been validated, and current efforts concentrate on strengthening reliability before advancing toward automated combustion control and broader commercialization. Addressing stability, reliability, and robustness will determine whether the technology can transition from a successful prototype to a scalable solution. The research suggests that smokeless chimney represents a technically grounded and environmentally relevant innovation. By prioritizing measurement reliability before full automation, the development pathway appears logical and responsible. The concept has moved beyond theory, and the remaining work focuses on engineering optimization rather than fundamental feasibility. As we close out, let's hear more from Aditya.
The system improves combustion efficiency by using real-time optical monitoring to guide airflow adjustments. The research shows the concept has progressed far beyond theory and now focused on reliable real-world deployment.